of Tony Yassin, and he kindly agreed to give a seminar on one of his recent works on quantum reservoir computing. So please go ahead.
Okay. Thanks, Luca, for introducing me, and thanks for inviting me. Also for arranging everything with the schedules and time. So hi, everyone. I'm a PhD student at ICFO. So first of all, I just see my screen. So if you want to interrupt me, just raise your voice. No problem at any time. But I don't see you if you raise your hand or whatever. Well, so ICFO is a super nice research institute close to Barcelona. So I put a map because many people think we are in Barcelona, but it's quite close. Like everyone lives in Barcelona. But the group is quite big, and I'm doing the PhD there since early 2024, so quite a bit of a time. Before that, I did my bachelor in Padua, and then my master in between Padua and Innsbruck. I did a bit of experience in industry in Candela in Paris, and now I finally settled down a bit in Barcelona, Spain, and yeah, that's a bit about what I did in the past. But today I'm going to talk about this work that was recently published. So the title is Harnessing Quantum Backaction for Time Series Processing. And this was done with other people at ICFO. So there are two people from Quantum Optics group that are Marcin, that was a postdoc, and now he's working in Kilimanjaro. That is a startup here in Barcelona doing quantum computing. Then there's Maciek, that is the professor and leader of the group, and two people from my group. So Tony, that is the leader of my group, and Pera, who was actually the last author of the work, so the main supervisor with the knowledge of reservoir computing. And it was like a team effort, so it's very nice to have worked with these people. Basically, the idea of the work is to say, can you find a way to show that there's a purely quantum effect, such as quantum backaction, that provides that is a resource in time series processing. So I'm going to try to guide you through what was the process. I will start with a brief introduction. I know that you also work in quantum reservoir computing, quantum extreme machine learning, so maybe I will repeat something that you already know, but I think it's still nice to get a baseline for everyone from which we can start to see what was actually our contribution. So just to start, we talk about time series processing, but what actually is time series processing? By time series processing, I'm saying whatever time series, whatever dataset that has a dependence on time, and such as speak recognition, you just record the voice, like the heart rate monitor or chaotic time series prediction. All these kind of tasks are related to time series processing. And I think it's always interesting to understand what is the state of the art, like how people are solving these tasks nowadays. And here I'm just talking classically. So the main solvers are some artificial intelligence-based architecture. And like on the left here, we have this architecture that is just a standard neural networks, but you have these recurrencies, and these recurrencies allow to your network to have some memories. So this is like the primer of the architecture, and these are called recurrent neural networks. And this was where these are kind of architecture allowed to start doing stuff with time series. And now we have all kind of super advanced models like ChatGPT. All these models, what they do whenever they generate something, they try to do it as a prediction of a time series. So basically, I would say that they're also doing some time series processing. And we all know that these kind of tools, they work very good, but we also know that there's a problem, that is the training. So training such models, due to the complexity of their architecture, is very expensive. And thus the community, the research community in computer science, came up with an alternative solution that is also called a training efficient alternative solution, and I will explain you why. And this solution is reservoir computing. So the idea of reservoir computing is that you want to use a dynamical system to process your data. So here you have the input data, that is this SK, that is input in a reservoir, which is parameterized by the state, that is xk. This reservoir can be anything, and it has some recurrent connections. And then you will extract the information to reservoir to produce an output. Why it is training efficient? It is training efficient because exactly the only thing that you train is the last layer that is in between the extraction of the information and the production of the output. Whereas before, you were training the whole architecture, so you're saving a lot of resources. And this seems almost magic. Like the first time I saw this, I was like, this is never gonna work because it's too easy. And of course, you have to impose some condition on your reservoir to make it work. And these conditions are that your reservoir has to need some memory. So the state of the reservoir needs to depend not only on the input that you're encoding in the reservoir, but also on the previous state of the reservoir. The dynamic of the reservoir has to be rich and nonlinear. You can imagine it such as you were talking about kernels in machine learning. The idea of kernels is that if you project your dataset in a high dimensional space, then doing inference become easy, almost linear. And the idea is the same. What you want to do is you want to exploit the rich dynamics of a system to solve a problem in an easier way. Then of course you need some dependence, some condition on the memory that you have on the system. And exactly these are the two conditions. That is that the evolution of your system has to be independent from the initial state and what we call fading memory. So basically what you're saying is that you want your system to have to remember more the recent input rather than the last input. If you don't have this condition, what happens is that your reservoir has infinite memory, and this cannot happen. So the idea is that you want to impose the condition to have a finite memory, and this finite memory has to be modeled as you have more memory of the recent input rather than on the past input. Once you have the condition, you can have all kind of possible system instead of your dynamical system. And this system can also be physical, like a photonic chip or some liquid. Or there were people doing this with an artificial octopus arm and using this system as reservoirs. So at this point, why not using a quantum system? And the idea is not just because we do quantum info, quantum machine learning, quantum technology, and we want to find a way to exploit our knowledge. But I think it's also, okay, of course, you can use all kind of quantum system if you engineer them correctly to have the properties to behave like a reservoir. But the reason for me is that, first of all, it is something that can be fundamentally interesting. As I said before, one of the features that you look into a reservoir is that you have a high space dimensionality, and this is something that you have embedded naturally in quantum system. Then you have something that you don't have in a classical reservoir, that are quantum effects. So you can understand if they play a role or not in solving your task. But this is just one point. Then there's a more practical why. And I think it's very similar to why reservoir computing emerged in the classical landscape. That is, if you want to do machine learning with a quantum system, what is the state of the art? So the state of the art right now, I believe, if you want to do machine learning with a quantum system, is to use parameterized quantum circuits. And they are good. Well, I'm just putting here a paper by Joseph Bowles from Xanadu, in which they were trying to benchmark and to see if these parameterized quantum circuit were competitive with respect to classical solver or not. And the answer they found in their paper, that I suggest you to read because it's very nice, was that actually they're not super good. And is the training expensive? And yes, we know that whenever you want to train such a system, you encounter a lot of difficulties, such as the barren plateau problem. So this for me is enough to justify a way of proposing we want to have a way to do machine learning on a quantum system that is training efficient. And this way can be doing reservoir computing with a quantum system. And if you really want to do quantum machine learning, such as machine learning with a quantum system, I think you could look into reservoir computing because of these reasons. So then it seems very nice, and we justified why we want to do quantum reservoir computing. But then you have to take into account that whenever you do stuff with a quantum system, you have some differences with respect to classical system. And one of these differences is that extracting information is not as easy as before, in the sense that now, whenever you extract information from a quantum system, you take a measurement, you have something that is called quantum backaction. Basically, whenever you measure a state, you know that the state will collapse in one of the eigenstates of the projector that you use to take the measurement. And this is a problem because you know that whenever the state is collapsing, so you have this disturbance on the system that is called quantum backaction, you're losing some information. But within the reservoir, we said that we want this information to stay in the reservoir such that we can solve tasks, such as predicting future steps of a time series. And to do that, we need the memory of the previous input. But if whenever we extract the information, this memory get lost, then we wouldn't be able to solve the task. So in the community, when there was the first proposal of reservoir computing, there was also some effort to try to understand ways to avoid this backaction, to preserve the memory. And now I'm going to present you a couple of protocols that they try to do that, and one protocol that tries to do things differently. So the initial proposal was done with something that is called the restarting protocol. The idea is that if you want to avoid backaction, imagine that you are analyzing a time series, you had a K input encoded in your system, and now you arrive at a point in which you have to measure. So you measure all the spins in your system, and you will lose a lot of information because all the states of this spin will be collapsed. Then for the next input, so for the K plus 2 in this plot, what I will do is that I will start again from scratch. So I will encode again all the previous inputs up to K plus 2. And now I will measure. So restarting in the sense that every time you want to extract information from the system, you reanalyze all the time series from scratch. And this works perfectly in the sense that the dynamics of your system that is mapped by the expectation values that you measure is like an unperturbed dynamics. The measurement backaction never played a role because you restarted every time. But you encounter something that is fundamentally limiting you, that is the time to process this time series that scales quadratically with the length of your time series, because every time you have to start from scratch. So then people in Mallorca, one of which Pera, that was working with me in the work I'm presenting, they thought about different protocols you could use to avoid this natural inefficiency in processing time series. And one of the idea was to say, as we said before, whenever we want a reservoir to be a good reservoir to do time series processing, we have to impose some condition, like a finite memory condition. Then if we already know that the reservoir has a finite memory, maybe there's no sense in restarting from scratch every time. But you can compute what is this length of the memory that we also call washout length. And instead of starting every time from scratch, you just start from the last input that you know that your reservoir remembers. This way, you can process every time the time series, repeating just a finite number of steps that is not the full length of the time series, but it's just this washout length. And this, if you do the math, turns out to be something that is linear in terms of the length of the time series, so is very efficient. And you can do the math and you can compute that since the reservoir at that point had no memory about the previous step, the actual dynamic that you're implemented is the same. So in both these cases, you manage to completely avoid the backaction and to produce what we called an unperturbed dynamics, in the sense that the measurement effect never plays a role in the dynamics of your reservoir.
Sorry, can I ask a quick question
Sure.
here? Possibly. Okay, sorry. So to say that this rewinding step has a linear cost, do you have to make some assumptions on the memory properties of the reservoir, or is this a general result?
So you know already that your system will have a finite amount of memory, and this memory won't depend on the length of the time series. So at that point, the result is general in the sense that you know that to process all the time series, you won't need something that is quadratic in terms of the length of the time series.
Okay, so basically you're saying that the actual memory will enter as a coefficient with this k, basically. Okay.
Exactly. Instead, before, since you have something that depends on the length of the time series, you don't have only a contribution that is linear, but you have a quadratic contribution because every time you have to repeat k steps.
But to actually use this rewinding efficiently, you have to know beforehand the memory, right?
Yes,
So I guess you do
something that
assessment.
Something that you can do very easily, and is like the test that you can do to verify what's the memory of the state of the system, is that you can initialize different initial states and see and start inputting the time series, and you look at the trajectories of the expectation value of some observable, and you see that at some point they will converge. And this meaning that you forgot the initial stage. At that point, you can start doing reservoir computing, and you know that the memory of your system will be exactly this length that is also called washout length.
Okay.
One question, but in this rewinding scheme, do you care about the starting state? Does it have to be a specific starting state, or it doesn't matter because it's...
It doesn't matter because you know that this is the exact length that allow you to forget about the starting state. So you can put the row 0 as if it was the row 0 that you put at the beginning of the protocol.
Okay, and I guess it depends also on the task you care about, right?
The initial state, you mean?
No. I mean, this rewinding scheme. I mean, if you have to do a task that depends on every time step, like, I don't know, parity check, maybe you have to have something.
Yeah. So in that case, maybe the memory that you care about, like in that case, parity check, in that case, you care about the whole time series. So it really doesn't make sense to cut. But if you are doing like a prediction of a time series, or you can do short-term memory tasks, like you're trying to remember previous time steps, you are imposing the condition on your reservoir that you have a finite memory to work, because if not, it's not working. And you can exploit this condition that you impose to make your protocol more efficient.
Okay, thank you.
Cool. Okay, great. So then there was another proposal they did that is inherently different from this proposal, in the sense that this proposal, as I said, they try to avoid backaction. So here, the dynamics, we call it unperturbed. But then you can do something that is also linear in terms of time, and we call it online protocol, in the sense that the system is never restarted. What's the difference? The difference is now the measurement doesn't interrupt this arrow as in the scheme that I showed you before, but is in between the line. So you can think about this measurement as an indirect measurement with a strength that is parameterized by the parameter g. So I will talk in the next slide a bit more about what is an indirect measurement, how we can think about it. But right now, just think about it as something in the middle. So you know that you won't be able to extract full information from your system, but you also know that you won't fully collapse your system. So you can have a trade-off in between the two. And this allows you to keep going with processing your information. So at every time step, you input your time series, you evolve your system, you measure, and then you input the next one, and you go on like this. And this is very nice, because from the first time you have something that is online, so you don't restart the system at any point in your protocol. And then you have something that is new, that is, you have a perturbance that is determined by the measurement process. So when this protocol was proposed, the idea was also to say we want to try to minimize these perturbance that we introduce, because we know, like the belief was that we know that this is the benchmark, the ideal benchmark. So we know that this is the top quality of inference we can achieve. So we want to try to do something similar, still online. And to do it at the best way possible, we have to try to reduce the disturbance that we introduce. And then I will talk you about what was our contribution. But first, just to dive a bit into what we call an indirect measurement, a way to think about it is just to think about a system where you have several elements. So you have a probe that can be a coherent pulse, a spin that can be either up or down, and then an interaction in between these two. And think that the interaction has a parameter that is like a coefficient of interaction, that is this g. So what you're doing, you're trying to measure the spin through a coherent pulse. And you know that depending on if the spin is up or down, you will have different statistics in the outcome when you measure. So the idea is that whenever you have a strong measurement, so whenever the coupling in between the probe and the system that you're measuring is high, you have two outcomes in the measurement probe that are very separate, so you can distinguish them clearly. Whenever you reduce the interaction in between the two, so in the probe and the system, these two distributions, they start to overlap up to a point in which the interaction is very small and you cannot really distinguish the two results. So you have less information than before. And I think this can help a bit to think about what an indirect measurement is. And this is also exactly the kind of model that we use in the simulation to actually implement this kind of process. So going on, what was like our main objective? The idea is what I said before. There are two kind of protocols, one that has tried to reproduce an unperturbed dynamics and another that is still efficient, but introduce some perturbance. And the idea is to debunk the belief that quantum backaction from measurement just negatively affect the performance of a reservoir computing. And how we do it, we do a bunch of numerics and we try to analyze different scenarios. And the key metric that we look at is exactly the performance ratio in between how an online protocol performs. So if I introduce some disturbance, what is this performance compared to the same system with an unperturbed dynamics? So either with a restarting protocol or with a rewinding protocol. As we said before, these protocols, they are not, they don't take into account the effect of measurement because they avoid them. So if we can show that at some point, the performance of a protocol with disturbance is better than the performance of the protocol without performance, we are very happy. And this is the main objective that we had in this work. And just to talk a bit about the details of the exact protocol that we implement, what we have is we have a time series, and we input the element of the time series into a spin system of 6 spins, and we input it in one of these spins through what is called amplitude encoding. So exactly this formula here. So essentially what you're doing, you're tracing out the 5 qubits, you're replacing one spin with the encoded spin, and then what you do is that you evolve the full system again, following a transverse field using Hamiltonian with all-to-all connection. You want to spread the information that you put on one qubit to the others. And once you did that, you can take a measurement. Then you go to the next input if you're doing the online protocol, and if this measurement is an indirect measurement. Instead, if you're doing a restarting protocol, what difference is just that you measure just at the last step, and in between you just input and evolve, input and evolve. But these are the main ingredients of the protocol that we use. Then what are the tasks that we look at to do a benchmark and to make our conclusions? So the first task that we do is like a forward prediction task. So basically imagine that I'm giving you an element of the time series and I'm asking, can you predict the element of the time series after eta steps? And for this time series, we take something that is called the Santa Fe time series, that is like a chaotic time series that is used as a benchmark in the dynamical system community. Instead, we also do the reverse. So we try to ask, given this time step, can you remember what was the element eta steps before? So this is a linear memory task that is called short memory task. And how can you compute how good your reservoir did in doing this task? Imagine that these S arrow are the target time series that we want to achieve. Instead, these S tilde are the one that we predict. What we do is we compute the capacity in between the two time series. That is essentially the square of the Pearson coefficient correlator. And this is just for a single task with a eta that is fixed. But if you want to have a more informative metric, you are interested not in just like one prediction distance, but you're interested in the how good your reservoir was in solving a series of tasks. So with eta going from 1 to capital N, for example. And if you sum all these capacities, so how your reservoir did in solving all these tasks, you obtain something that we call the sum capacity. So essentially, in the ratio that we had before, here in online and rest rewinding, we have some capacities of the reservoir. And then going to the results, here are some results. So these are color maps. At the top panel, we are putting the data for the first task that I described you, so the forward prediction task. Instead, at the bottom panel, we have the short memory results. And in the y-axis, we have the interaction strength. So if the G is very small, essentially you are not extracting information from the system, and you're also acting with a very small disturbance. As you increase G, you have something that around 4 is almost a projective measurement. So almost if the system are like very coupled. In the x-axis, instead, we have the dynamical parameter of the reservoir evolution, that is the external field of the transverse field using model. And in color, we plot this performance ratio that I told you about. So if the color is dark red, we are very happy, meaning that the performance, like the disturbance that we introduced in the dynamics, is helping the reservoir in solving the system. If the color is white, meaning that they are performing almost the same. And if it's blue, meaning that the unperturbed dynamics is performing better than the perturbed dynamics. So the important thing here is that we are assuming a system where you can actually tune the interaction of the strength of the measurement. And this is mainly the new ingredient of what we do. Like we assume that you're able to control and optimize the strength of the measurement. And we want to show that if you're able to do that, you can find a measurement strength that allow you to perform better than if you had no measurement effect. So here you can see that in both plots, you have some dark red regions. So you have some regions in which you have a disturbance introduced by the measurement that helps you in solving the task that I told you about before. And if you just take some cuts, so these lines, and you plot them individually, what you can see is the details of this performance. So here now in the y-axis, I'm plotting the sum capacity, and the red line is just the unperturbed dynamics, so the restarting protocol. Instead, the blue lines are the online protocol, so the one with indirect measurements. The light blue is the one in which I don't optimize the measurement strength. So I just say I want to process online, but I don't care about optimizing the measurement strength. Thus, I just have some result that if you look in comparison to the red line is not working a lot. Instead, the dark blue line is the line in which you take an optimization through the strength of the measurement. So you are controlling how much disturbance you're introducing. And it's evident that there's some gap at the beginning that is like this red region, meaning that for some region, the reservoir without measurement effect is performing very badly. But if you introduce some measurement effect, this helps you in solving the task. Moreover, if you look at the maximum performance, you can see that even the optimized reservoir with the optimized measurement strength can reach the optimal performance that was reached by the unperturbed dynamics. And okay.
Sorry,
Yep.
in practice, the optimization is something that you can do some way in efficient way, or is something that you
Yeah.
can do theoretically, but then in practice is hard to.
Like you can think about like the standard technology for doing quantum computing that you have this superconducting qubit. So whenever you do a measurement in superconducting qubit, what you're doing is literally the model that I explained you before. Like you have a coherent pulse that is a probe, and you have your spin that is your transmon. And whenever you do a measurement, you never do a projective measurement because you have two systems. You have no way of doing a projective measurement. You're always doing an indirect measurement. And you have to, the difference in between a weak measurement, so a measurement that is not very informative, and an almost projective measurement is the length of the pulse that you're applying to take the measurement. So the length of the pulse is something that you can engineer very easily in the electronics of your control. And imagine that you do a shorter pulse, you're doing a less strong measurement. If you do a long pulse, that is what they do to do projective measurement, you're doing an almost projective measurement. So this is something that is, I would say, is also a justification of the why this is important, because whenever you do a measurement on a quantum system, practically you're always doing an indirect measurement. And in most of technologies, you're able to tune the strength of the measurement quite easily, like in this example I made.
Oh, okay, but what is the optimal pulse? I guess that is not easy to determine given arbitrary dynamics.
The idea is that you do the optimization in simulation, and then you can apply the optimal pulse. Of course, if you were to do the optimization on the system, then I guess it's a bit more resource. You have to require a bit of more resources.
Okay, but to simulate, I mean, this is not really scalable. I mean,
no, sure.
Okay.
But at yeah,
okay.
I would say that this is a feature of how it works right now, and I don't think that is unfeasible to think about doing a small optimization routine on the hardware, even at large scales. Of course, I see it unfeasible if you want to do a comprehensive analysis. Okay, like here, every point is average over 50 realization. This, I wouldn't predict someone doing this, but maybe just a short scan of sweep parameters and having a guideline that you can estimate more or less classically. You know where to look. You take these few measurements, you collect results, and then you select the optimal.
Okay, thanks.
One question, like, so here I can see that your online protocol is better than the full Fuji Nakajima is the full one, right? Protocol, I guess. But why for low H? What was H? Was the transfer field strength?
Yep.
I mean, is there a physical reason behind that, or I don't know? Because it feels weird to me that you're adding noise in a sense, and it's better.
So I wouldn't say that is always, like, I wouldn't say we're adding, okay, it is noise to some effect, but so the understanding of like why it works, like why the gap is greater for a smaller H and why the gap is almost closed further on, is that, at least to me, the understanding is that whenever you have a larger field, your performance is also, at least for example, in the top panel, you are reaching the optimal performance. So there's really little thing you can do to increase it. But then in the small H regime, you have your restarting protocol that is working very well. Like over 20 tasks, you're performing an average of 5. So you're almost not solving the majority of the task. And in this case, you can see how adding this backaction can help you. Maybe in that case, the disturbance they introduce actually helps you to scramble a bit more the information that you have in the system. And then, of course, if you just look at the best performing reservoir, I would say you don't have such of a gap. But you have a situation in which maybe you are obliged to stay in this regime of small h, and then you already know that doing the restarting is very resource inefficient. But with the online, also, apart from being more efficient, you also have this disturbance that is introduced that helps you. And this is also something that was shown in a different modeling with the dissipation, for example.
Okay. No, I mean the thing is that there is, I think, a phase diagram for a dynamical phase diagram. I don't know.
Yeah.
So I think that part, I mean, the small h part is literally the same as the regime, as a specific regime of quantum observer computing, right? So I don't, it depends also on the J, on the couplings.
Yeah, so here the J is fixed, and we can recover the exact behavior of the paper you're mentioning. That is the paper by Rodrigo Martinez, and this explains why just looking at a single line, you have less performance for a small h. You have a maximum performance around the phase transition, for example, for the short memory task, and then you have a lower performance afterward. And then the thing is that even if you have the same behavior for all the 3 lines, what you have is that whenever you introduce the backaction, for the region in which the reservoir is performing not at the maximum of its performance, you can perform better.
Okay, that's more clear to me. Okay, thank you.
Okay.
Sorry, just to understand, this is the sum of capacities in the 2 tasks, right?
Yeah.
And so you are taking eta equal to 20. You said that in the top plot you get the better performance.
So for in the top plot, we take we take all the possible. So whenever you imagine that in the paper, there's the plot of the capacity of the single task, and in the x-axis, you have the different distance in predictions. And we just go up to when the distance in prediction, like the capacity for a distance is 0. So for the top task is around 50. So here is the sum of 50 different contributions. Instead, here is the sum of around 20. So 20 different contributions. These are different tasks, so they have different maximal contribution, let's say.
Okay, thanks.
Okay.
Also, sorry, just one. Go ahead, Luca. I just said mine is fast though.
Fine.
Okay. Like the number of resources is the same, right? You are using the same state with a total number of shots, I guess.
So that's the next slide. So basically here we are working in an ideal infinite resources regime. So here we are just taking the expectation value of the system that we can do them from density matrix simulation. So it's a bit of an unfair comparison in the sense that here we are not talking about the efficiency of the protocol. This is just, imagine you can somehow extract the expectation value of your system with infinite shots. So something that is not feasible. But then when we go to finish shot regime, we know that we don't only have the effect of the measurement effect, but you also have the effect of the finish shot, because one protocol is more efficient than the other.
Okay,
so last one. Actually, you partially already addressed what I was going to ask, but another thing I don't fully understand. So this G, you can understand it as a coupling strength with some auxiliary system that you actually measure, right?
Yeah.
Okay. So G equals 0 here corresponds to the restarting or rewinding whatever protocol, or is it something different? So G equals 0 means there is no coupling with the actual thing you measure.
Exactly. So this is something subtle, because you have to differentiate what is simulation-wise and what is like more formally wise. Because G equals 0, if you look in the plot, G equals 0 is just a line that is dark blue. Okay, so this is 0 in the metric that we are using, because whenever you have G equals 0 in the online protocol, is meaning that you are not measuring the system at every time. So you're having random data, basically.
Okay. Yeah.
Then in practice, since we are doing a simulation, putting G equals 0, we can still extract the information because we are in simulation. We don't apply the measurement effect matrix that models the perturbation. And we have the result for the restarting protocol. That is the unperturbed dynamics. And this is a more efficient way to simulate the restarting protocol rather than starting at every step.
But okay, so, but G equals 0, if you measure the auxiliary system, you get no information, which is consistent with what, not getting nothing. Whereas the restarting protocol, you would be measuring, let's say, magically measuring without perturbing the actual evolving system instead of auxiliary system, right?
Exactly.
Okay, and so maybe you're gonna address this then. But so G very close to 0. When it works, you also have to take into account that the actual sample cost will go to infinity when G goes to 0 here, right? Because at some point, when G gets closer to 0, your measurement is weaker and weaker, which means you're getting less and less information, which I would guess would also mean you need more statistics to actually infer what you need.
Yeah, so then because of this, then the next step in the analysis is to do something at comparing the number of resources that you require for each protocol and capping the same number of resources for the two protocols to effectively have a comparison, like a practical comparison of, does it really make sense to reach this regime that seems very small for the G, or it doesn't?
Okay. Yeah. Sorry.
Cool. Thanks a lot for the questions. So as I said before, this analysis is done just extracting expectation values, but this is not something you can do on practice. So then what we did was like, okay, imagine you have a finite number of shots. So first thing you have to do is to differentiate what were the two protocols that we were gathering in the same set of unperturbed dynamics protocol, because now you have a different efficiency in between the two protocols. We said that the restarting protocol has a quadratic efficiency and the rewinding protocol has a linear efficiency. So first of all, we compare the online protocol with tunable measurement strength with respect to the restarting protocol. Now, if we set a finite amount of resources, we have to take into account that since the restarting protocol is more inefficient than the online protocol, setting a finite time to perform the experiment, you will have more shots for the online protocol with respect to the restarting protocol. And this is the relation. So the relation is that the number of shots that you have for the online protocol will be proportional to the number of shots that you require for the restarting protocol up to a constant that is the length of the series that you are analyzing. And there's the math in the paper, and I think is very intuitive. So now if you do the same plots as before, you're not plotting just the effect of the measurement backaction, but you're also plotting the effect of the scaling inefficiency of one protocol with respect to the other. For that, it doesn't make sense anymore to just plot the difference at every dynamical parameter regime, but we want to say something stronger. We want to try to say whenever the perturbance that you introduce provide an advantage in the case in which you are performing at the maximum. So just to make it easier, imagine that here you have the blue line. In this new plot that we are analyzing with the performance metric that we call performance ratio, the minimum performance ratio, we won't do a ratio in between these 2 points with the same x-axis. But first we do the red line, that is the unperturbed dynamics. We take the maximum of this line, and then we divide every point of the blue line to this value. So this is something, so there's this maximization in the middle. So this is a stronger plot in some sense, and you can also see that the advantage is smaller because of this. But here you're saying that comparing the two, where the measurement effect is helping you in the case in which you care about the maximum performance and you have finite resources. So here you see that still you have some regions in which the perturbance that you're introducing is helping you. But of course, this is not just the measurement effect. This is also the scaling. So then what you can do is to say, okay, put apart the restarting protocol that we said is inefficient. Let's focus on the rewinding protocol that now has the same efficiency. Here, there's a typo. There's no scaling in this point. But now what we say is that, okay, we compare the performance ratio that we had before. We take the maximum value that we had from the plot, and then we plot it at different number of shots that we have available to understand if the advantage is something that we have just at infinite a number of shots, or if it also appears at a finite number of shots. So ideally, if you increase the number of shots, you expect to recover the same color map at the beginning. But you can also show that even for a finite number of shots, you have the performance ratio that is more than 1. So this is very nice. And this shows that even at finite amount of resources, you can recover this advantage due to the measurement backaction. So
sorry, this is the number of shots per run of the machine. Okay, yes. So every time you run, the protocol is 1 shot.
Yes.
Or, okay. Is the whole time series that you run once is 1 shot?
Yep.
Okay. Thank you.
No, sorry. See, yes. So basically, yes, because you run the time series is online. So for every time step, you took a weak measurement, and this is 1 shot. But then this number of shots per measurement setting. So this is the same you were saying.
Okay. Okay. Thank you.
So that means that for every measurement run, you have a single outcome for every weak measurement. Is that what you're saying? Or when you say 1 shot?
And this is 1 shot.
Okay.
And then, yeah. And then you basically at the end you have a data set where every run you collected k results and number of shots. So you do averages over these k results.
So when n is 10/5, you send 10/5 times the entire training time series.
Yes. Okay. You are collecting expectation values in the end, as if you were in a standard protocol.
Maybe a bit of a technical thing, but to actually to simulate this, if you're, I mean, when you simulate the weak measurement, you apply the formalism with the map, right? Like I'm looking at the paper with this L applied to the state.
Yeah, yeah.
So how do you, so to simulate a single measurement shot, that means that the state updates depending on that single event you measure at that step, right?
So there's a trick here that is, since in the end we compute expectation values, what you can do is that you can compute the average effect of the measurement perturbation on the map, and then you don't have to care about single trajectories. But so if you look in the paper, there's a matrix that is called M, that is the measurement perturbation matrix. And there's some math behind that tells you that if you have n to the s trajectories, what you can do is that you can evolve the density matrix. At every measurement, you apply this measurement perturbation matrix. You collect your expectation values like that. Then afterward, to take into account of the finished shot, you can introduce some statistical noise in the expectation values, and they exactly match the result of the single trajectories. So this was a work done in the previous work by Pera in Mallorca. And this is a very nice trick, because if not, to simulate every, like already to simulate all of, like every point is a 50 iteration of a 50 different reservoirs. But if you had to do it through single trajectory, this would be very computationally expensive. But through this trick, you can do it more easily.
Yeah, makes sense. Thanks.
Okay, cool. So I'm almost at the end, I promise. We were very happy with this, but then of course the referee was not, and he asked us to do other stuff. And the other stuff was very nice also. and was to say, okay, now you compared with the literature that you knew that was from previous collaborators, but actually other people have worked on providing hardware efficient online protocols for reservoir computing. How do you compare with them? And them was especially this PRX Quantum by Kobayashi, where they were proposing an online protocol in which they had just a circuit realization. Every time you have your spin system, you input your time series, you evolve and you measure. At this point, you deleted all the information, and the next step, you again input the next step, but now you have a feedback that is a classical feedback. So given the expectation value that you collected before, you apply some unitaries, and they depend on this expectation value that you had before. And this way, they were saying, like what they say is that we provide a protocol that has memory, and this is true, and is online, and this is true, and helps you to have an hardware efficient way of doing reservoir computing online. And this is very nice, but it's also very different from what we do, in the sense that by doing some classical feedback, essentially, you are not able to fully recover the coherencies in your system. And what we believe in reservoir computing is that the main memory of the system, of the previous time steps, is hidden in the coherencies of your density metrics. Then by doing indirect measurement, I'm partially deleting these coherencies, but I'm not fully deleting them. By measuring and then doing a classical feedback, what you're doing, you're completely destroying them, and then you're not able to recover them. So for us, it was natural to think that our system had an advantage with respect to them. And then we did the numerics, and this is actually what you see, in the sense that this is like a short-term memory task. This is the prediction of how far you want to remember. And these are very different iterations of their model with different feedback strength. This is a parameter they introduce. Instead, this is our optimal performing online protocol. And we see that we can recover, we can solve the task longer than them. So we were very happy of this, and we can say something like, if you want to have an online protocol, having an indirect measurement protocol is better than just having a classical feedback. And just to conclude, what we have is, like we showed, that backaction is not essentially always something bad for reservoir computing. You have something that is an advantage or a positive effect even in the finite resource scenario. Of course, as I just said, in between online protocols, we think that with respect to classical feedback protocols, indirect protocols can be preferred for the reason I told you about. And then there's the real question of like what it would be interesting to understand better, and we are trying to do that, but it's not easy, is really to understand mathematically how the measurement effect is modifying the dynamics such that the reservoir performs better. At the same time, we are working also something different that is hopefully out on archive next week, but it's always not like that. That is a hardware implementation on a Qiskit of this protocol such that you can run it and make it available for everyone. And this is something else we've been working with Rodrigo Martinez that now is in Donosti, but previously was in Roberta Zambrini's group in Mallorca. So that's it for me, and I'm happy to take any question.
Sorry. Thanks, first of all. Really, really nice talk. About the Qiskit implementation, I mean, this is just Python package, let's say. It's not something that you can run actually on the machine, right?
No. We do things on the machine.
And how do you implement the weak measurement in that case?
So you do that through ancillary qubits. So imagine that your probe is another qubit. You have a coupling between them, and you can map the exact same map of the model that we have here, but in that different setting.
And okay, and but I expect that in order to be weak, this requires a lot of ancillary, right? Or not? Or
no. So the idea is that imagine you have two qubits now. One is the main qubit and one is the ancilla. So if the two qubits are initialized in the same state, Then whenever you have the C naught, if you measure the ancilla, you have the collapse also in the main qubit. But if you have a different initialization in the ancilla qubit, you have that the collapse is not the full collapse in the main qubit, and you can tune this given the initialization of your ancilla. But I mean, the details will be out in the archive. I'm happy to send it to you whenever it will be out. But yes, it works.
Okay, sure. That's interesting. That would be nice. Thanks.
Maybe another question. Can you go back to the slide where you had the performances with finite resources?
This one or this one?
Yeah, no, the other one. Yes.
Okay.
So here, the bottom plot in particular, this shows that if for very small g's, you get good performances, right? That's the meaning of the, like, say, red region.
Yeah, yeah. This blob. Okay.
Yeah. Okay. So do you have any intuition there? Like if G is very, like we said before, if you said before, if G is 0, you're measuring noise there because there is no count, right? If G is very small, at some point you're measuring no noise, you're measuring something that is close to noise, though. Like there will be some information about the actually evolving state, but very little of it. So with finite resources, it will be hard. I mean, it depends how many resources you use, but it will be harder to distinguish relevant information from the noise, right?
Yeah.
So for me, it's a bit weird that I mean, I don't know what's the scale of G that makes something strong or not, but very small G's at some point shouldn't work very well.
Yeah. So here, for example, is G maximum around 0.5. If I don't remember correctly, this is 0.3, 0.5. The thing is that the dependence. So I told you I like to think in this practical picture. That is how the framework to simulate this works. So the measurement effect is just a matrix. Okay, imagine it, and the dependence on the element of the matrix on G is an exponential to the square of G. So if G is very, very little, I agree with what you're saying, like 0.05, you are doing noise. But then you have a slope that is very big. And then already at 0.2, if you just plot the functional of the element of the matrix that you're using to do the disturbance, you have something that is not at 0, but is already towards non-zero values. That is like quite significantly also statistically. So maybe if you think about it in a linear way, I agree with you that you think, okay, but here you will just have noise. But then if you understand how G is embedded in the dynamics, so you have this double, like exponential to the square, already a G of this magnitude is doing quite a lot.
And how does this plot change with the statistics? Like this is fixed statistics 10 to the 6, if I'm reading correctly, roughly.
Yep.
Do you know how this changes, like you do, I don't know, 10 to the 3, or you like increase or lower the statistics? Do you know how this changes, roughly speaking? Like for low statistics, for example, I would expect it to work less good for small G, I guess, right?
Yeah. I mean, imagine that you have less statistics, you won't have any region because basically everything is noise.
If it's too small, okay, sure.
Yeah, but so we chose 10 to the 6, not randomly, but because we know that at this resolution in terms of finite shots from the previous study that was done, you are able to have some results that make sense and they're just not just noise. So you are well above the signal to noise ratio.
But now, like the signal to noise ratio depends on G itself, right? Like there's not a fixed value of statistics that will always overcome that will always give you this regime.
Sure. But like for the regime we are considering, so G in between 0.2, 0.5, this thing. we know that this number of shots, they make sense.
Okay, so should one expect that increasing the statistics, this red blob maybe goes further down or something like that? Because it becomes easier to let's say usefully use information even for very weak couplings.
Yeah. So now here is a different metric, but in the paper there's also this same metric with infinite shots. So you can see how it changes.
Right. Okay.
Sorry, can you hear me?
Yeah, sure.
Sorry, I have maybe some stupid questions, but for the sake of understanding, can you go back when you define the